Okay, let's get started. So it's a great pleasure to introduce today's colloquium speaker, Gonzalo Torroba. Gonzalo is also a Canada visiting professor at Hanna program in honor of our late colleague Stanley Hanna, a nuclear physicist. Brings eminent scientists such as Gonzalo for extended visits and lectures. Gonzalo, let me give a kind of extended introduction to him and his work. He did his undergraduate degree at the Gonzalo Institute in the mountains of Argentina, where he is now himself a professor and researcher. This institute is amazing. It overachieves both in generating physics and physicists. There's a huge diaspora of Argentinian leaders in the field that come out of that place. And it's funny, when we're working remotely, often Gonzalo is headed off to do a problem session with students. And I think, although it's kind of a thing here, I think they invented the flipped classroom way before us, and they also do it, for example, in the quantum field theory class. I joke about doing that here, but they really do it, and it shows. Okay, so his history after that was to get his PhD at Stanford University in 2009, before joining us here at Stanford for a 5-year postdoctoral fellowship, where he drove collaborations with many people in the department that have really stood the test of time. He's made major contributions to the field with a very diverse interest and very diverse toolkit, ranging from condensed matter theory to cosmology. From the very beginning of his career, with things like Douglas at Rutgers and through his time here and the current times, he's had an epic research program to understand the formula of quantum gravity in a way that's consistent with the observed lambda CDM cosmology of our universe. And he's achieved milestone results in this direction, including modeling it concretely and simply in string theory, counting the microstates and serious microstates of the cosmic horizon, that sort of stuff. But at the same time, and in parallel, he's done amazing work in condensed matter-inspired theories, the condensed matter-inspired quantum field theory, where working in clever limits of large numbers of degrees of freedom, he and his collaborators have managed to control infrared strong coupling physics of interest for transport phenomenon and such things. And if that's not enough, he has a major program homegrown on, again, in quantum field theory and its intersection with information theory. And I think that's what we're going to tell us about today. It's just a joy to interact with Gonzalo. I've had that pleasure for many years. Everyone who does so has the same smile on their face when they do that. And I do hope everyone here will get a chance to take advantage of all this here. But for now, let's just enjoy this presentation.
Can you hear me from there? Okay, great. Yeah, thank you very much, Eva, for the very nice introduction. And also thanks again for the HANA Scholar program for making possible my visit here. So the title here is a little bit technical, but the colloquium is really going to be about what we can learn of quantum field theory by using ideas from quantum information theory. Okay, so because of that, let me start trying to say why or motivate why do we want to have a colloquium on QFT. Sorry, yeah, okay. And so the main reason we want to understand better QFT is that because it's a framework that is common in many different areas of physics. For example, in high energy physics, of course, we know that from the unification of special relativity and quantum mechanics, then QFT is born, and the best understood model we have, which is a standard model of elementary particles, is a QFT. QFT is also very important in condensed matter physics. Also, as Eva just said, basically there we think about the lattice with quantum degrees of freedom, but if we can tune to a regime where the correlation length in this lattice is much bigger than the lattice spacing, then we can think about averaging those degrees of freedom, and then we get an emergent effective quantum field theory description. The picture below is basically a cartoon for cosmology. Understanding the history of the universe also requires quantum field theory in many key steps. including, for example, the origin of all the structure that surrounds us, that is quantum mechanical. And finally, the picture we have there on the right-hand side. Okay. The pointer. Okay. Anyway, so that's a cartoon supposed to mean that we think that even quantum gravity is at the end described by quantum field theory or maybe quantum mechanics also. Okay. So because of this, understanding properties of quantum gravity is simultaneously important in many areas of physics, and we want to make progress along this direction. Now, something that is very challenging in many of these systems we are showing is that they have strong interactions, and because of this, they develop emergent phenomena. And so it's often very, very hard to understand these systems using perturbation theory or even sometimes numerical assimilation. Okay. So for example, the types of questions we would like to understand in this system are, for instance, given some basic input information like the dimension of space where we are, the matter content and the symmetries that the theory has, then what are the possible non-perturbative behavior of the theory, so what are the phases, for example. Or
I could see your cursor maybe.
Okay. Yeah, no, it's fine. Okay. So that's one type of question we'd like to understand, and maybe a little bit more generally, at a more general level. So can we prove that there are laws in QFT that tell us what can and cannot happen? Maybe, having some kind of thermodynamic analogy in mind. Okay. Now, I press OK there, so we don't have that. Good. Okay. So one of the most promising ways of understanding QFT is the renormalization group. Here, the idea is that the quantum field theory is viewed as an effective theory. That means that this effective theory comes equipped with some short distance cutoffs, and we don't know what happens at some shorter scales, but we have a framework to tell us how to slowly increase this cutoff by integrating out short distance modes in order to get an equivalent effective theory that is valid at longer scales and can reproduce the same observations. Okay, so that's called the renormalization group. So the picture there is from Kenneth Wilson, which was one of the main proponents of this. And although, of course, in general, it's very important to be able to solve specific Hamiltonians we care about, the RG brings kind of a complementary perspective, which is that it becomes important not just to think about the specific Hamiltonian, but also about the space of couplings where these runnings happen, the fixed points that appear in this RG, and the trajectories that connect them. So this is a cartoon illustrating dots. So you have there, for example, these black dots. By the way, this cartoon is taken from the review by Wilson. So these black dots symbolize the fixed points of the RG, and by fixed point we mean that if you change the scale of the cutoff, the theory doesn't change. So the theory is actually scale invariant. So integrating over short distance modes doesn't change the long distance observations. Okay. And so we can imagine starting from some of this scaling invariant fixed point, perturbing it by some relevant interaction that will produce some flow in the space of couplings, and those are the trajectories you see there. Okay. So we want to start to think about this structure. Okay. And maybe one nice thing about this way of thinking is that although these systems are very far from classical, they are at zero temperature, they are very quantum, still the RG makes nice connections with statistical mechanics and thermodynamics. Okay. And in particular, from the beginning, there was this idea that the RG is basically an irreversible process. Okay, I was told at the beginning maybe it's a tautology. So indeed, so the tautology is that so we keep losing degrees of freedom when we keep increasing the distance cutoff because we are integrating over microscopic modes. So this was a very important piece of intuition that came from this way of thinking. Okay, so we keep losing short distance modes. Okay, but if you want the challenge is how to make this idea precise, because of the reason that in the continuum limit we have an infinite number of degrees of freedom. Okay, so we would like to make this more mathematically precise. Okay, so in fact, something similar happens in thermodynamics, where we have some underlying system with some huge degrees of freedom, but still we can think about like equilibrium states, and to this equilibrium states we can associate functions of state, such as, for example, the entropy or the free energy, and then we have statements such as the second law of thermodynamics that tells us what can happen to the entropy or the free energy, for example. So we would like to understand field theory in in somewhat similar terms. So the question would be, can we introduce a function of state that we associate with this scale invariant fixed point in this algebraic picture, and then can we prove that this function of state can only, for example, decrease or increase under possible algebraic flows? So that would be a notion of reversibility we can try to prove in QFT. Okay, and surprisingly, 40 years ago, there came a paper that gave the first mathematical proof that this is indeed possible. This is a beautiful 2-page paper by Alexander Samolochikov, 1986. And there, as the title says, he established the irreversibility of the flux of the renormalization group in a 2D field theory. And 2D means one space and one time dimension. Okay. And essentially what he did is he proved that there exists a function C of G, so a function C that depends on the coupling. And this function can only decrease monotonically along an energy flow. And moreover, at the fixed point, this function is a function of state that we know. It's something that's called a central charge. So it's some property of the fixed point. He was considering a little bit of special fixed points, which are not just scale invariant, but have a bit more symmetry. They are these conformally invariant fixed points that you see below at the end of the answer. Okay, so here we'll also be talking a bit more about conformal theory, but you can simply think of this as just as something like scale invariant, but it has a little bit more of symmetry. Okay, so this was the first formal proof of the idea that QFT is irreversible, and it actually started a lot of progress in the area since the last 40 years. Okay, and then maybe 20 years ago, something surprising happened, which is that it became clear that actually quantum information theory provides, in some sense, a natural framework to try to understand this question. Okay, and perhaps coming from the thermodynamic side, the fact that quantum information should be helpful for QFT is not surprising because it provides a natural way to transport thermodynamic reasoning into the quantum world. Okay, so basically the goal of this colloquium will be to tell this history about how quantum information allows us to make progress in understanding the laws of QFT. So that's what this colloquium is going to be about. And we'll do this in 3 steps. So in the first step, I'll give a review of what we need about quantum information, so that this is self-contained. And then I'll discuss how this leads to a proof that relativistic quantum field theory is irreversible. Okay. And in the last part, in the introduction, I was also mentioning condensed matter and cosmology. So in the last part, I'll try to start making contact with systems that are more interesting to condensed matter and cosmology because they don't have this Lorentz invariance, the relativistic QFTs. I'll be talking in part B. Okay, so this is the plan. Please let me know if there are any questions at any time. We can discuss. Okay, so let me begin with what we need about quantum information. So, and again, if you haven't taken QFT1 and QFT2, don't worry. As I said, for our purpose here, QFT is something that we can think as in models in condensed matter physics. So there's some lattice with quantum degrees of freedom, for example, spins that are shown there. There is some lattice spacing called epsilon that you see here. Okay, there. And moreover, we want this lattice system to have the property that the correlation length is much bigger than the lattice spacing. So you can think about averaging over these quantum modes, and then you get some effective, continuum field theory description. So that's the way QFT arises in many condensed matter systems. In high energy physics, sometimes we like to think that this lattice is actually a regulator, although it can also appear for other reasons, for example, related to gravitational reasons. But if we really want to think of this as a way of regulating the theory, I'd also like to say that all the results I'm going to present can also be understood without this regulator, but then you need a bit of more mathematical machinery related to something called algebra QFT. But we will actually not use this mathematical machinery in this colloquium, so we will be happy to think about this lattice that is sitting there. Okay, so we have this quantum system, it lives on the lattice, and we imagine it's in a pure quantum state. And for this talk, this pure quantum state is going to be the ground state. Okay, so something can be generalized to the excited states, but here we'll stay with the simplest, just the ground state. Okay, and now the way that quantum information enters is that we start asking questions about the subsystem of this lattice. Okay, so here we have drawn, for example, a region A, and so by subsystem we mean that we are going to restrict all our observations just to be related to observables that have support in this region A. So we can only make measurements in region A. Okay, so it's not that we are putting some physical wall surrounding this region, just some virtual wall, but we only have access to a subsystem of the full pure quantum mechanical state. Okay. So as we know from quantum mechanics for open systems, then the formalism to understand this introduces a density matrix. Here the density matrix is denoted by rho A. And essentially the definition of this density matrix is that it allows to compute all the expectation values for elements inside that region. So by definition, the trace of rho O has to reproduce the expectation value of O. Okay. And essentially, maybe a more intuitive way of saying what this density matrix is that we start from the pure ground state, so the 0, ground state that you see there at the bottom, and you think about tracing over, say, all the spins that are outside your region. So that will produce some mixed state. That mixed state is described by density matrix. Okay. As I said, this is a formalism that is general for open systems, but here it's a bit more specific. First, because we start from a pure state in this local lattice and we are tracing over degrees of freedom outside of it. And then because it has a geometrical mean, right? And so this subsystem is actually associated to the region of the lattice. And we'll see that this is very important because the density matrix basically provides a bridge that allows to understand these quantum mechanical properties of the lattice in terms of geometrical properties associated to measures that we can compute out of this density matrix. So it's very useful because it provides this quantum geometric bridge, and we plan to use it. Okay. So basically, quantum information theory starts from this density matrix and then computes certain measures and hopefully can prove theorems about properties that these measures satisfy. So the first and most famous measure we can compute is the von Neumann entropy. So it's defined as minus trace follow rho. Okay, so probably you have seen this definition before. And intuitively, it basically measures the lack of knowledge of the exact state we are in because we only have access to a subsystem, or maybe said differently, it measures the entanglement with the tracing over the degrees of freedom that are outside. So this was introduced by von Neumann in 1927, and we can understand this actually using two other pieces of information. The first way to understand it will be just to diagonalize the density matrix. So we write it as the eigenvalues there that are pi, and then the eigenvectors is II basis. And then if you plug this diagonal form of the density matrix inside the von Neumann formula, you simply get minus sum of pi on pi. In other words, you get a classical Shannon classical information. Okay. Now here it's curious to know that actually Shannon introduced this entropy in 1948, so actually 20 years after von Neumann. So it's kind of curious that in some sense, quantum information theory predates classical information theory. Although of course both were kind of different. Okay. But anyway, so that is one way to understand the meaning of this von Neumann entropy. And another way we need to compare with what happens in thermodynamics. So imagine now again a subsystem, but now that subsystem is kept in thermal equilibrium because it's in contact with some thermal reservoir. Okay. Then in that case, the density matrix has this Boltzmann distribution with e to the minus beta h, where h is a Hamiltonian and beta is the inverse of the temperature. Then if you just plug that in the von Neumann formula, it simply represents the thermodynamic entropy. Okay, so we have these three notions and they are essentially connected by the same formula. Okay, but it's nevertheless important to point out that this entropy can have really parametrically different behaviors across different systems. Okay, so here I've made a simple table. So for example, in a quantum free body system, typically the von Neumann entropy would be some multiple of log 2. So each entangled pair contributes something of order log 2 to the entanglement entropy, and then we have, say, n entangled pairs that will be n log 2. So this is some small number. Maybe the extreme opposite limit of this free body quantum information calculation would be a mostly classical and big system. There, the entropy, like this thermodynamic entropy, scales at the volume, right? And some factor that depends on the temperature. Okay. And now we are going to get into QFT. So now I'll show it, but then we'll explain it. So QFT satisfies a formula for the entropy, which is actually very different from the thermodynamic entropy. It scales like the area of the subsystem we have access to. So the area in units of the lattice spacing. So that's the epsilon squared there. Okay. And I'll just say that although we are not going to talk about gravity in this colloquium, as far as we understand, even in quantum gravity, this area law holds. Okay. but it's made finite because this lattice cutoff is replaced by the Planck length. Okay. So, good. Okay, so now we're going to get into this area law for QFT. So we want to understand what it says and then how to deal with it. So as I said, this is really one of the fundamental discoveries in quantum field theory, so the validity of the area law. And it ultimately is telling us that there is some huge degree of entanglement. So just to make it more precise, let's imagine we are in 3 space dimensions and our subsystem is a sphere of radius r. So we only have access to making measurements inside this sphere of radius r, which is represented there. Okay. And so basically, what is the area divided by epsilon squared is basically the number of fundamental elements you have there tiling the sphere of size epsilon. Okay. So basically, the area law is telling us that essentially there is 1 qubit of information per lattice area in the boundary of the Planck region. Okay, so that's what it says. And there below, I've shown the same formula, but just in d dimensions, because we'll be jumping a little bit across dimensions in this talk. So in d space-time dimensions, then the area goes like r to the d minus 2 and in units of the upper panel of the cutoff. Okay. So the history of the area law is, so it was first proposed, as far as I understand, by Bombelli, Cooley, and Sorkin in 1986. But really, the person that put the finger on it and its relevance, how to compute it in flat space, and provided, I think, a very clear understanding was Srebnicki in his 1993 paper. And he also, noticed, as well as the previous author, he noticed, connections with black hole physics. And this really, the discovery of this area law really is part of the big revolution in our understanding of QFT, also in our understanding of quantum gravity by using holography. One of the main motivations beyond the holographic principle, and also it's extremely important in condensed matter physics. This area law because, for instance, many of the important numerical methods that are used there heavily exploit the validity of the area law. Okay. Okay, good. So having understood this area law for entanglement, let's discuss in somewhat more precise terms what is the structure of entanglement entropy at these fixed points of the renormalization group. And as I said, we are going to be looking at fixed points that are not just scale invariant, but they have a little bit more symmetry. They are conformally invariant. Okay, so these are, for example, the fixed points that arise naturally when we combine scale invariance with Lorentz invariance. But they are also of interest in other areas, and they appear, for example, in condensed matter physics as well. Okay, so we have these fixed points, and here I've made a list of what happens in different space-time dimensions. So the first dot there is d equals 2, so 1 space dimension. In 1 space dimension, we are looking at a subsystem, which is just an interval. Okay, this R. And then one can show that the entanglement entropy goes like C times log R divided by epsilon. And it turns out that this C that appears there is the same as homologic of C. So this paper I showed in the picture at the beginning of the introduction. So we start to make the connection. Okay. And this is again the central charge of the conformity theory. Then we have d equals 3, so 2 space dimensions there. The system is a disk. It is R. The first term is the area term, R divided by epsilon, so it's the perimeter of this disk. And the second term is called F. And then in 3 space dimensions of the line below that, you see the area term we just discussed in the previous slide. And then there is a following term, which is also again a logarithm, the same way that it equals 2, and the coefficient is called A. Okay. So it turns out these 3 quantities that appear here, the C, F, and A, they are finite quantities, so they don't depend on the lattice cutoff that appears there. And they are intrinsic to the fixed point. And by intrinsic, we mean that they don't care about how we got to the fixed point. So we can just define it, just having information about the fixed point and not having information of the RG that got us there. Okay. And as I said, they are finite, they do not depend on the lattice regulator. So they are the natural, candidates for these functions of space or RG charges that we can associate with 6 points. And they will provide, a mathematical notion of this number of degrees of freedom that we would like to show that it always decreases. So for example, just to give some intuition, if we have a free model, for example, say non-interacting bosons in 1 dimensions, then if these bosons are massless and we have 10 bosons, then C is 10. And if some of them become massive, they should be coupled from the long distance observations because the correlation functions are exponentially suppressed. If two of them are massive, then C goes from 10 to 8. Okay, so that's a very simple algebra flow where we see that C increases. But of course, the challenge is that if we are in strongly interacting models, we don't have this intuition of just counting which of the fields that are relevant for making the algebraic calculations and the observation. Okay. But nevertheless, this mathematical notion, this mathematical quantities C, F, and A, they abstract this idea of just counting what are the relevant number of fields, okay, which is finite, and how that decreases along the RG. Okay. But now you see we are in a little bit of a trouble because we would like to isolate these terms C, F, and A, but although in 1+1 dimensions, this C term is the leading term in time entropy because the area of an interval is just 2 points. Okay, you see that in the following dimensions, for example, in 2 dimensions and in 3 dimensions, actually both F and A are completely subdominant compared to the area log. So the area log is this gigantic contribution, and we would like to see if we can isolate this tiny piece from this gigantic contribution that counts the number of relevant fields or the number of relevant degrees of freedom. Okay, so the challenge is how to separate, how to split the area term from these functions of states we would like to associate in QFT. Okay, and if we can do that, then can we prove that these guys, C, F, and A, can only decrease along the RG? Okay, so that would be the program to actually show that QFT obeys irreversibility laws. Okay. Okay, and there is one last step I need to do in quantum information. I need to review this idea of the quantum relative entropy. Okay, and this relative entropy is a measure of distinguishability between now two density matrices. Here they are called sigma and rho, and it's defined as trace rho log rho minus trace rho log sigma. So now we are talking about two states we want to compare, and if you want maybe the classical way of saying what this relative entropy is that if the distribution, if the true distribution of some model is sigma, but we think it is rho, then in n trials, the probability of confusing rho and sigma goes like e to the minus n times relative entropy. Okay, so in that way, it's like an information-theory way of distinguishing these two density matrices. Okay, and this is also a very natural object that we want to think about QFT, because in QFT, when we say, oh, we want to prove that the number of degrees of freedom decrease, really in the back of our minds, what we have is a comparison between what should have been the scaling invariant theory and this other theory that keeps changing along the RG. Okay, so they both have, say, for example, the same Hilbert space. There are some spins, there are some observations we can do there, but we are perturbed one Hamiltonian by some interaction, and that produces a renormalization group flow. So we would like to compare the two observations in the two theories that have the same Hilbert space, and these two Hilbert spaces, they define two states or two density matrices, which are sigma and rho. So here in this colloquium, sigma is going to be the density matrix of the scaling invariant fixed point, and rho is going to be the density matrix of this theory we'd like to understand that follows the renormalization group. Okay. And maybe one last way to understand this quantum relative entropy is that in this quantum information context, there is a way to introduce a Hamiltonian, but it's not a physical Hamiltonian. It's more like an information theory Hamiltonian, sometimes called a modular Hamiltonian. And the idea is that associated to this scaling invariant fixed point density matrix sigma, we can write it as e to the minus h. We can always do that because the density matrix is positive, definite, and Hermitian. So we can always introduce an operator h defined like that. The denominator there is just for normalization purposes, so don't worry. So for example, if the system were in a thermal density matrix, then H would really be the physical Hamiltonian. Okay, yes.
Do you need a UV fixed point, or can I just define a theory with
You can define it in all cases, but what I'm going to do next requires that I say, I have two density matrices, so just one of them I'll write as e to the minus h, which is C. But this can be done for any density matrix, indeed, yeah. There is always some kind of information theory Hamiltonian. If you run thermal equilibrium, it would be the physical Hamiltonian, but in general, it's not. And it tells us, what's happening to the degrees of freedom inside your subsystem. That's this H. Maybe we could also use a different letter like K, but whatever. So here I just want to say that if in the previous formula where it says sigma, I write e to the minus beta h, then the relative entropy acquires this following structure. So it becomes trace rho h Remember that rho computes expectation values. So trace rho H means the expectation value of H in the density matrix rho, minus trace sigma H, that means the expectation value of H in the state, associated to the scaling variant fixed point, and then minus delta S. Delta S is the entropy of rho minus the entropy of C. So in other words, the relative entropy is actually a difference in energies, these information theory energies, minus the difference in entropy. So in other words, it's a free energy in thermodynamic analogy. Okay, so that would be another way to think about this, what this relative entropy is doing. It's a difference of free energies. Okay. Okay, and the main motivation to introduce this quantity is that we can now state what is the main, maybe the most important result, or one of the most important results from quantum information theory, which is called the monotonicity relative entropy, or strong subadditivity of the von Neumann entropy. And the result, so this theorem goes as follows. So consider a system made out of two parts as a bipartite system, AB. So it has two parts, and we know how to divide the vector space of state into two parts. And then we have two different density matrices. So rho AB and sigma AB. Okay. And now there's a procedure called partial trace, which means we take rho AB and we trace over the degrees of freedom AB to produce a density matrix that now is rho A. So it tells us what are the measurements in A. So that's called partial trace. So we just trace over B. And the same for sigma. So we start from sigma AB and we do a partial trace over the subsystem B. Then monotonicity of the relative entropy is a statement that the relative entropy needs to decrease under partial trace. Okay. So this theorem was actually proved for the entropy, as we're going to review next, by Liam and Buscai. The pictures are there in 1973. And around the same year as Ullmann was thinking about the same thing in terms of relative entropy. And I think his paper is from 1977. But this is like one of the really most important results in quantum information theory. And for us, what this brings is a formalization of the idea of forced graining in QFT. So if you want, the intuition is that if we trace over one of the subsystems, we are now restricting to a smaller region. By restricting to a smaller region, we have less observables available to us to distinguish the two states. And because we have less measurements we can make to distinguish the two states, then the relative entropy needs to decrease. So that's it from some piece of intuition behind this theorem. Okay, and another way to state this theorem is directly in terms of the von Neumann entropy. But to do that, we need to think about a system that has three parts. Here they're called A, B, C. Okay, and then this monotonicity property that we want is comparing rho in ABC to now a tensor product. So rho A times rho BC. Now you take that, you trace over C, same formula as before, but now you're just tracing over C. Then you erase C basically on both sides, and so that relative entropy needs to be bigger than the one obtained after partial trace. Okay, again, the same monotonicity formula, but this one is very nice because if you just plug it in the definition of the relative entropy, you get that all the energy terms, so this Hamiltonian terms will cancel out, and you simply get an inequality now directly from the von Neumann entropy. And that inequality is a formula at the end of the slice, which says that the von Neumann entropy of AB plus that of BC is bigger than the entropy of B. So notice that B is the intersection of AB and BC, and ABC, which is basically the union of AB and BC, and that's what's called the strong subadditivity of the von Neumann. Okay. Good. So what follows now in the colloquium, or the main message will be that by importing this formula into QFT, we'll be able to learn important laws that are satisfied in full generality at an approximative level in this two theory system. Okay. Okay, great. So now we are ready to start discussing irreversibility in QFT. As I said in the introduction, we'll first do it for relativistic QFT, and then I'll make some comments about systems, for example, in cosmology or condensed matter physics. Okay, so here we're considering a unitary quantum mechanics model, which is in the continuum limit, and it's also Poincare invariant. So Poincare invariant means that it's translational invariant, and it also has a series of special relativities, so there are transformations. So after many years of work, it turns out that this is the right question to ask. So the question is, when is monotonicity of the relative entropy or strong subadditivity saturated? So that turns out to be the right first step in this direction. And here I've written that in formulas. So the inequality wants saturation, so it becomes now an inequality. So the first one is the one for the relative entropy, and the second one is the one for the von Neumann entropy. So intuitively, the question we are asking is, in which situations can we trace over subsistence, and in which situations can we coarse grain without losing information, without decreasing the distinguishability? So that's what we are asking here. It turns out that this question has a classical analog. One can show that this saturation of the monotonicity of the relative entropy at the classical level means that we have a probability distribution that satisfies the Markov property. So in other words, the conditional probability of A, so A condition to B and C is equal to A condition to B.
It needs to go down fast. So
Yes,
the analogy is what the going forward in the classical Markov chain is analogous to renormalizing.
The analogy is, so in the Markov chain, so if you want, we can forget about how C is related to AB. In the quantum analogy would be that if we trace over the subsystem of C, we are not losing information about our state now. We are anyway being able to reconstruct exactly the state. So in other words, coarse graining becomes a reversible process. We can undo the process. But if you want, yeah, maybe if you give me 1 minute, because in the next slide I'm going to, yeah, yeah. Okay, good. So because of this classical analogy where we have these Markov processes, these states that saturate monotonicity of the relative entropy, they are called quantum Markov states. Okay. And just to elaborate a little bit more on what's the intuitive meaning of this. So if we have a Markov state, for example, sigma, then basically, and we have this three-partite system ABC, is telling us that the entanglement between A and C is in some sense only mediated through B, because we can trace over C, and then we still get the same distinguishability measure. Okay. And moreover, one can prove, and this was work by Petz and also by Patrick Hayden and collaborators who studied more the structure of these states, one can prove that monotonicity is saturated if and only if the modular Hamiltonian of this density matrix, I'm putting it again here H, so H is minus log sigma. So the modular Hamiltonian in the full tripartite system, so in ABC, can be exactly reconstructed by knowing the modular Hamiltonian in the smaller subsystem. Okay, so this would be a case where we have exact reconstruction of a state in a bigger space by knowing the state in smaller space. So in some sense, it's telling us that the entanglement is trivial enough so that we can reverse the process of tracing. Okay. And now, so in 2017, we basically realized that this can indeed happen in PFT. So the question is, are there Markov states in PFT? And the answer is yes. These Markov states, they appear in these conformal field theories that are they describe the fixed points. So we think about one of these fixed points in their ground state, okay? And then it's possible to reconstruct the state in a bigger region by knowing the state in a smaller region, but only if all the regions involved in the equality there turn out to be in a common light cone. Okay, so you think, so for example, before we talked about, say, a disk is inside a light cone. Okay, so for example, a point that is to the future of the disk, and we can consider different regions. Okay, and the condition is that all the boundaries of this region, they need to lie on the same common light cone. Okay, so the proof is a little bit mathematical, and I'm not going over it, but basically it's a theorem that these CFTs with regions whose boundaries they all lie on the same light cone, their ground state is a Markov state. So there we can just partially trace, and it's completely reversible. So it's an exact reconstruction of the state, okay, from knowing it in smaller subsystems. And maybe just to give a bit more of intuition, what is behind this property is that basically this information theory Hamiltonian, actually it becomes almost like a physical Hamiltonian on the boundary. So it turns out to just act like one of these Lorentz boosts of special relativity on the boundary of the entanglement region. Okay. Good. So this is now a general property of quantum field theory, more particularly of conformal field theories. In quantum field theories, it's valid at a non-perturbative level. It's associated with these RG fixed points. And now we're going to basically go ahead and show this irreversibility formula, and we're going to apply. Okay, so I should say there were previous instances, at least irreversibility had in QFT. I alluded to them in the introduction. So 20 years after the result of Samological, so in 2004, Cassini and Huerta were able to prove the same Samological theorem by using quantum information. Okay, and that's when people started to realize that quantum information should be important in order to understand the RG. And then in 2012, they proved the successor of the C theorem in one more dimension. So now we have two space dimensions. And then the analog theorem is called the F theorem because it goes to this F quantity. Okay. And basically, what we did in 2017 is find a formula that is valid for every dimension. And in particular, it applies using quantum information theory to the so-called A theorem, which is valid in 3 space dimensions. Okay. And here I'm just going to give you cartoons of how the formula is proved. And again, it's a little bit mathematical, but the intuition is just combining the ingredients which I've discussed before. So the idea is start from your disk or your sphere, your entire region, but now boost it a little bit. So if you boost it, because Lorentz symmetry is a symmetry of the theory, you get the same von Neumann entropy. Okay. So now start from 2 regions, so the red one and the blue one. These are 2 spheres, and they are boosted. And they have been boosted to lie on the same light cone. I'm just drawing, because I cannot do some multidimensional pictures, I'm just drawing cuts of these spheres on the light cone. But we have 2 regions, the red one and the blue one. Okay. If you compare to the strokes volatility formula before, say the red region is AB, the blue region is BC in the previous formula. And then you apply strokes volatility. That means that the entropy of AB, the red region, plus the entropy of BC, which is the blue region, should be bigger than the entropy of the intersection. The intersection is the red curve you see in the middle of the picture there, plus the entropy of the union, and the union is the blue curve, which is the one you see there. And here again, by intersection and union, I mean in the sense of time evolution. So whatever you can predict using time evolution there. But then you see a problem because both the intersection and the union develop kinks. They develop like vertices where there are some singularities, and one has to control what happens there. It turns out that that's the place where this Markov property I said before enters. This Markov property turns out to be able to smooth these kinks. Okay, and then we can basically replace the entropy of the intersection and the entropy of the union smoothly again by spheres, which is what you see in the right-hand side.
Yes, as this, I want to understand what I don't yet.
Yes.
Whether we're talking about a hypothesized Rho and sigma, we're talking about a hypothesized quantum field theory,
Yes.
we're talking about a hypothesized fixed point of a renormalization group,
Yes.
we're talking about hypothesized renormalizability.
Yes.
What are
Yes.
the hypotheses?
Yes. So we are within the algebraic framework. So we start from some conformative theory that
What's
uses
conform?
the UV fixed point. So we start from some fixed point that is a conformative theory, and we imagine perturbing it by a relevant operator, so it's indeed within generalizability. So what are all the things that happen in the AR once you perturb this fixed point by some relevant interaction?
Okay.
So that's the setup.
So this is a statement about conformal field theories that are relativistic.
Perturbed,
And
Yes.
it's general.
yes, any conformative theory that is relativistic. Yes, anyone, and then perturb it by any relevant operator you want. So it's renormalizable in the context of conformal perturbation theory.
Gotcha, now.
Yes, anyone. It's not modeled again. So we only need
Okay, so I understand the
Yeah.
statement now. It's a general statement about
It's a general
conformal fixed points. Okay,
Yes.
now. Can you help me a little bit about what it means physically?
yes.
Suppose we found such a thing. What
Yes.
would be aside from just restating the fact that it's a conformal field theory, that's.
No,
that's
good.
a point, that's.
Yes.
That's
We-
relativistic,
yeah.
what else is there?
No, we of course, we have simple examples. For example, in 3 space dimensions, we can start from a free theory and perturb it. For example, QCD would be an example of that. You perturb it, and then it becomes strongly interacting. In 3 dimensions, actually, all the examples we know of a CFT that then you perturb, well, okay, the CFT could be strongly coupled, but if you start from 3 models, then you need to use gauge case.
What I'm trying to understand is whether this property is different
Yeah.
or the same as
Good, good.
postulating conformal fixed point and relative.
It's different. Yeah, yeah, it's not
So
obvious.
one goes one way, but not the other. So,
It-
you have a theory with these symmetries, then this property holds, but the reverse is not the case.
So indeed, so if you have conformal invariance plus renormalizability plus unitarity, so this conformal are unitary, then you can prove that this property is true. It's a theorem that you can prove, well, a physics theorem.
Gotcha, but the reverse is not the case.
The reverse meaning that if this is true, that you can establish, yeah, no, the reverse, as far as I know, is not true. Yeah, yeah. Yeah, thanks for the question. Yeah. Okay, good. So, yes.
At what point you introduce time in these concepts? Is when you say there is a Markov chain?
Well, I have unitarity. So, for example, you can have as in statistical mechanics, you can have models that are fairly invariant, but they are not unitary or they are not reflection positive. And if you don't have unitarity, then this is definitely not true. Yeah, so I need time evolution to be unitary. Yeah. But okay, so the theorem is the last line here. Basically, I was going to say, when this red curve becomes very, very close to the blue curve, so the areas become comparable, and actually these inequalities, they become a differential inequality. And the theorem says the relative entropy derived twice with respect to the area is upwards concave, or the difference in entropies derived twice with respect to the area is downwards concave. Okay, so it's basically a concavity property very much in the direction of thermodynamics, but now valid directly in quantity theory. And again, for all the flows that you can obtain from any general CFT by perturbed by a relevant interaction. So it's kind of intuitive that the area should appear there because, as we said before, the area is basically measuring the density of qubits that appear in the boundary of the intermediate. So, for example, the second inequality there says that, and again, delta S is the entropy of the perturbed theory minus the entropy of the scale invariant theory. So it says that the, entanglement in the perturbed theory should decrease fast enough so that it's concave. So that's what this theorem is saying. Okay, or if you want to look at the first inequality, it says that the distinguishability between rho and sigma should increase fast enough so that again upward concave. And now we're going to see how that implies the irreversibility theorem in PFT. So we just applied this concavity formula to the three cases I listed before. So the entropy in 2 dimensions, in 3 dimensions, in 4 dimensions. So here again, imagine you start from some CFT in the UV that has some central charge. You flow to some other CFT in the AR that has a different central charge. So in between, the entropy is not going to have that form. It's going to have some complicated form. But near the endpoints, it behaves as CUV times log R or C infrared times log R. You apply this theorem, you just do one integral, and you prove that CUV is bigger than CIR, which is, of course, a logical theorem from the introduction. Okay. In 2 dimensions, you apply the same theory here, and now it becomes more non-trivial because you see, this formula we had before had 2 derivatives with respect to the area. Okay. So this is precisely getting rid of the area term, which is what we wanted to isolate these functions of state in PFT. So the area term in 2 dimensions is the first term, so R divided by epsilon. So that's the second formula there. Okay. You take 2 derivatives with respect to the area, that term is easy. Okay, and then you are able to access the sibling term, which is F. So in between F, of course, changes with size and so on because there is an energy flow, but you integrate this quantity, you prove that FUV is bigger than F. And the same in 3 dimensions. So in 3 dimensions, we have an area term. After the area term, we get this function of state, which is A, they want to isolate. The one we want to isolate, you take 2 derivatives, you take to the area, the first term is killed, and you prove that AUV is bigger than A. Okay, so these are the so-called CF and A theorems. And so to summarize, what this proves is that for relativistic PFT in 1 plus 1, 2 plus 1, and 3 plus 1 space-time dimensions, we can define functions of states or RG charges that are associated to these conformal fixed points. These RG charges are C, F, and A in different dimensionalities. And furthermore, an energy flow is possible only if the charge in the UV is bigger than the charge in the A. Okay, so that's the mathematical notion of irreversibility we're able to prove. Okay. And here I should also say that as well as there was a proof of the C theorem in 2 dimensions, there were actually 2 proofs, one by Samologico and one by Cassini and Huerta. Then Cassini and Huerta proved the F theorem, And then in 4 dimensions, maybe 30 years after Samologikov, there appeared a proof in line with Samologikov's proof using operator methods of the A theorem. This proof was done by Margowski and Freeman. So basically, and there the quantum information proof was missing, and we provided it with this formula. And this formula is also the same in all dimensions, because in every dimension it just says take 2 derivatives with respect to the error, and that should be concave. Okay, so that's the irreversibility law for QFT, and I'm almost done. So I just want to make 2 comments. So of course, it's very much an open direction of research to extend these results to QFTs that appear in condensed matter physics and cosmology. And the reason is that these systems have less symmetries, and having less symmetries, their RGs are less constrained, they are richer, and they also harder to understand. Okay. But I just want to mention 2 examples where we are able to say something about irreversibility. The first example is related to adding impurities or defects or boundaries to these quantum field theories. And here there is a very nice and important example, which is the Kondo effect, condensed matter physics. Okay, and the Kondo effect, for those of you who don't know, is simply, at least in its simplest form, it's electrons in a metal that are interacting with a magnetic impurity. And basically, Kondo showed that the coupling, this magnetic coupling of impurity, grows due to quantum effects. So this is really a beautiful phenomenon. It's actually, in some sense, the first example of asymptotic freedom in 3 dimensions. So before QCD. Now, people try to understand this better, and they came up with a more general formalism to understand these types of problems. Among many people here, there were Affleck and Ludwig that pushed a lot for developing this. And this formalism is called boundary conformal theory. So the idea, in the case of the Torroba model, is take your electrons in the metal, okay, for this impurity calculation, you only care about the spherical symmetric configurations of the electron. So you can just do a spherical reduction, and then the 3-dimensional problem becomes the problem only along the radial direction. So it becomes a 1-dimensional problem that starts from r equals 0 to r equals infinity, and the impurity sits at r equals 0. Okay, so then we have massless fermions in 1 dimension that are an example of a conformal field theory. But now this conformal field theory has a boundary, which is at r equals 0, and that's where the impurity sits. So you need to put boundary conditions there. And that's why this is called boundary conformal field theory. Okay, and then the Kondo model in this language would be, okay, let's perturb this conformal boundary condition by a relevant interaction, localized only at the boundary of the CFT, and let's see where it goes. Okay. So this is now another example of an RG, but it's qualitatively different from the previous one, because the boundary degrees of freedom are undergoing the RG, but of course they are talking to the bulk. So for example, they're exchanging energy with the bulk. So it's not guaranteed that the previous irreversibility laws would hold here. Okay. Actually, Affleck and Ludwig were, I think, the first ones to conjecture that this should be irreversible, in the sense that one can define something called the boundary entropy, so some notion of entropy we can associate to the impurity, and this boundary entropy only can decrease along the flows. Okay, that was in fact proved at finite temperature by Freeman and Konechny, and then various years ago we proved it at zero temperature using quantum information theory, using very similar methods to the ones I showed before. Okay. And that was this, by thinking about the Kondo model, that's actually how we came to realize that it was very important to think in terms of the relative entropy in QFT. Okay. And here I'll only mention that, so this would be an example where you break some of the symmetries. So for example, you break translation invariance and you break boost invariance, and nevertheless you can prove that this irreversibility property holds. And this has been generalized, so this area, irreversibility formula I showed before can actually be proved for d-dimensional defects embedded in high-dimensional CFTs, even though the RG is kind of different. Okay, and the last thing I want to show that I'm done is how about cosmology. So I'm here by cosmology, of course, cosmology has gravity, but here I mean understanding quantum theory in, say, a fixed cosmological background. That's extremely interesting and fascinating. Again, very much still an open problem. We have new things happening. For example, we have time dependence, we have cosmological horizon, we have no global notion of energy. So what can we do there? Okay. So recently we started trying to understand some non-perturbative properties of QFT in the sitter. The sitter is the simplest cosmological universe. So it's there is some picture here on the left. So it's some universe that both towards the past and the future. It expands exponentially, but it does so in a very symmetric way. And it's of course also very interesting for observations because the period we are about to enter now with the late time acceleration is well modeled by the sitter, and also the inflationary period is also modeled approximately by the sitter. So it's important to understand what happens to QFT in this background. So here something very interesting happens, that is because the space grows so quickly, actually an observer does not have access to the full space time. They can only see part of the space time because by receiving light rays and shooting light rays, it only can see a finite region, which is shown there. That region is called the static patch in the sitter. So that's an example where quantum information is useful because, again, we have, from the point of view of the observer, we have an open system. It turns out that this open system is described by some kind of thermal bath. So the density matrix there is of the Boltzmann form, e to the minus beta h. Okay, and so in this setup, we ask, okay, what happens is now we have a conformal theory that undergoes the analogy, but this QFT now lives in this space-time. So what's an opportunity dynamics of this quantum mechanical model? And we were able to prove by considering subsystems such as the one I showed there, right? Again, we consider some sphere or some disk that is sitting inside the causal patch. We compute the von Neumann entropy, the relative entropy. Is it irreversible? The answer turns out to be yes. And it's the same answer as in flat space. So you can prove that for QFT in the sitter, for subsystem inside the static patch, again, this concavity property of the entanglement entropy is exactly the same as in flat space. So strong relativity is powerful enough not only to jump across dimensions with d equals 2, 3, and 4, but it can also help you understand what happens with QFT in curve spectra. Okay, so that's the last point I wanted to make. So we are done here. I hope I try to convey the idea that quantum information is really a nice tool to understand the RG in QFT. In particular, we focused on establishing properties of irreversibility of RG flows, and there we really make strong use of monotonicity of the relative entropy and properties of the von Neumann entropy. This is a nice subject. Many open, and non-trivial problems remain. For example, still we would like to go beyond this kind of highly symmetric models and look at QFTs with less symmetries. For example, what happens with two impurities or more impurities? That's of course extremely different than quantum physics. We still don't know non-perturbative laws we can prove there. Okay, or what happens in, say, less symmetric cosmologies? Same. We also know that there are QFTs that are outside this paradigm established by Wilson. So can we try to access them or understand some of the properties using quantum information theory? Okay. And also we have some suspicions that maybe there can be something actually stronger than strong relativity. We have some quantum field theory hints about that, but yeah, maybe there's something to think about there. Good. So I just want to end by saying, thank you to a few people. First, my group of really great collaborators in Bariloche, Horacio Castillo, my work and postdocs and students. Also my the research council that is paying for my research, and by Sarah Institute where I teach. As I said before, really special thanks to the HANA Scholar Program that allowed my visit here. Without that wouldn't have been possible. And also really special thanks to my host Eva for so many years of great collaborations. More to come, and also all the colleagues at SITP, now LITP, for always being so welcoming and providing such a nice and welcoming environment. And yeah, thanks a lot. Yeah.
Thank you so much, Gonzalo, for that beautiful talk. We have time for questions.
Yeah.
You said towards the end that relativity or open invariance is not fundamental, right?
Well, we went, for example, I showed you one example where we broke it in a controlled way. Like
you have it.
Yes, yes.
I would go one step further. What's special about quantum field theorems? Would you have this in a non-linear classical field theory?
Well, I mean, for example, we were using unitarity, and we're also heavily using locality. For example, if you have some local lattice model, then I don't know what to say, for example.
But classical field theories can be local, but usually local. It's just non-linearity, so it's not that trivial, and you need symplectic kind of evolution to replace reality. So in principle, you could demonstrate things with the classical theory in principle.
Yeah. Well, in a sense, for example, thermodynamics is an example.
Yes.
Yeah. In a sense, this is like trying to generalize the thermodynamic laws, but it is very quantum world, which is PFT. Yeah.
And many quantum physics you can do mean field and that with classical physics.
Yeah.
They're nonlinear and you have irreversibility in some way. Like
Yeah,
this.
Yes.
In the de Sitter case, you quoted an inequality for delta S, but not for the relative entropy.
It's also for the relativity.
It's also.
Yeah, I just was running out of space. Yeah.
I have a question for somebody who does not know much
Yeah,
about
sure.
theory. In what sense is this whole argument different or nuanced from like the second law of thermodynamics? What is the difference?
In some sense, it is like a second law of thermodynamics, but it's new. I mean, it's not that this, for example, this type of like these two inequalities, they don't follow from the second law of thermodynamics. They require new ingredients. For example, I had to use this structure that I said at the beginning. I had to use this Wilsonian way of understanding PFT, where I start from a fixed point, but this fixed point needs to be conformal. For example, if the fixed point is scaling invariant but not conformal invariant, this is not true. So you really need to put more ingredients. So I'm using that. I'm using unitarity and I'm using Lorentz invariance. Yeah.
Thank you.
Yeah. Thanks for the question.
Any more questions?
Yes, please.
This Wilsonian view that you're talking about means basically that down there you always have more degrees of freedom. So you have infinite degrees of freedom in a certain way.
Yeah, that's okay. And here it's measured by the area term, but
Yes.
really the challenge is to extract something like this is, for example, like what you would call a specific heat. So it's just how to extract some finite measure of what are the relevant fields that contribute at the given scale. Yeah.
Just think about the relative scale to a given scale, and it's saying something non-trivial about balance states, right? And you can't have a bazillion balance states at some scale.
Yeah, right. Yes.
Is a non-trivial state.
Yes. Yeah, thanks.
Not complete dynamics, but one way of saying it.
Yeah. Right.
Great, any
Okay.
other questions? If not, let's thank Gonzalo for a great.
Okay, thank you. Thanks.